Today, I would like to talk about ultrafast amplification, mainly optical parametric amplifiers and the optical parametric chirp-pulse amplifiers, OPA and OPCPAs. So what is the motivation? Why do we need ultrafast amplifiers? Only a limited number of gain media are suitable for high-power, ultra-fast lasers. Okay, but why? Why the gain media is so rare that it can be used in ultra-fast amplifiers? Excuse me?
Fast delay.
Delay? Oh, okay, you mean the energy levels you can have. Okay, right. Anything else? In theory, any material has energy levels, right? But you have to select media with proper energy levels such that you can have the stimulated emission at the desired wavelengths, right? And there are some practical issues. For example, crystal growth. 你挑的这个 gain media， 它不一定很容易用累晶的技术长出来，长出一个很好品质的晶体，所以不那么容易。There are thermal dissipation issues. Remember, when we talk about high power amplifiers, the average powers could be hundreds of watts or even kilowatts. So thermal dissipation is an important issue. Okay, 不然你的晶体很容易就烧毁啊，你没有办法得到 high power. Anyway, there are many challenges you have to overcome, such that the gain media will be useful. And nowadays, the most matured ultrafast oscillators are of two categories. The first one is Tai Sulphide oscillators. Central wavelength is about 0.8 micron. Typical pulse duration is about 25 femtoseconds. You can have shorter one, like 7 femtoseconds, if nonlinear broadening is used. Okay. 你只依赖 Tai Sulphide 的先天的 gain bandwidth, maybe 这个数字比较容易取得。那你要靠一些非线性机制，such as cell phase modulation, as we discussed in the class. Sometimes you can have shorter than 10 femtosecond pulse duration from the Tai Sulphide oscillators. The second one is ytterbium doped fiber. Central wavelength is 1 micron. Pulse duration is much broader, like 150 femtoseconds or 250 femtoseconds. But in either case, the pulse energies are about 10 nanojoules from the oscillators. 从振荡器出来，没有经过额外的放大，你通常可以得到的 pulse energy 大概就是这个数字。Okay. But with these ultrafast oscillators, we cannot meet some requirements. For example, we do not have mid-infrared light source, okay, which is very important in spectroscopy and multiphoton imaging. We talked about spectroscopy at the beginning of this semester, right? Do you still remember what is spectroscopy? Molecular identification, right? How do you know the species belongs to some material? You can check the absorption spectrum, okay? Just like the fingerprint. Usually, especially the gases, 我们有兴趣的一些气体，它的 absorption spectrum 都在这个 range, mid-infrared. Wavelengths maybe 3 to 8 microns. But you see, Tai Sulphide, you have 0.8. Ytterbium doped fiber, you have 1 micron. It's much shorter than mid-infrared. Okay, so we need something more. Also, high energy applications such as machining or extreme ultraviolet laser generation. In these applications, the pulse energies have to be much stronger than just 10 nanojoules. Okay. 所以问题有两方面哈，一方面是波长没有办法到我想要的领域，另外一个是能量不足。OK， 所以使得你只依靠这个 oscillators sometimes not good enough. Now, how to change the central wavelengths? Okay, you can find a new gain medium. Okay, if you can, but it takes time and effort to do so. And this is case-by-case solution, which is unfavorable, right? For example, in some application, maybe you need 3 micron lasers. So you need to spend a lot of effort searching for some gain medium, which is lasing at 3 microns. And if you are lucky, you get that. Next time, if you want to use 5 micron lasers, you need to repeat the process. And usually, it's very difficult to be successful. Okay, so that's case-by-case solution. Is there any once-for-all solution? Besides, transitions between real energy levels, just like this figure, 4-level system, we use it in lesson 1, for example, has finite bandwidth and involves with heat dissipation. Just use this figure. Why there is only finite bandwidth? If your gain median has a 4-level system like this, which factor determines the gain bandwidth you can have? Remember, lasers you need stimulated emission, right? So where is the stimulated emission? Yes, between these 2 levels. And how to determine the corresponding gain bandwidth. If it is like this, what is the bandwidth you can have? 0, right? If level 3 and the level 4 are truly narrow lines, no uncertainties, then transition, stimulated emission, S here, right, involves with only 1 possible photon energy. So your gain bandwidth is 0. Okay, but in reality, they are usually not exact lines, but dense lines slightly separated with each other. That's manifold. 所以你可以想象，这其实不是一条线哦，这是一群很密的线，这也是一群很密的线。So the combinations could be of many possibilities. That's why you can have more than 0 gain bandwidth. Okay? But do you know why they are group of lines instead of exact lines?
Is that energy degeneracy?
What is degeneracy of your meaning?
Because there are several orbitals for electrons, and each orbital can possess slightly different energy.
如果是那样，它通常是指分得很开的能阶啊，比如一颗原子，它有好多个轨道嘛，照你的说法，那通常不是，这个就是其中一个轨道，这是其中一个轨道。那个例子会给你分得很开的这个轨域或者轨道。
我的意思就偏向说，比如说像以前在高中的时候，比如说3P 轨域啊，那可能就有3Px、3Py，然后3Px² y²。 那这三个轨域如果根据外面的磁场的
Okay, keywords comes. Okay, external field. Without that, you have exact lines, exact energy levels. 3P 各个3P 的 energy 应该一样嘛？那个是由那个3决定，对不对？那为什么你会有不太一样、稍微不一样的这个能阶或者是轨域？因为有外在的 field。一旦有外在的 either magnetic field or electric field, there is energy level splitting. That's called Stark effect. OK， 那你就会有一群了。But the question is, where does the external field come from? ，Okay, come from the material itself, right? That's right. Instead of applying an external field, we did not do that, right? 你不会故意拿一个外在的电场或磁场去这个套在你的 gain medium 上，你不会这么做。Material 本身它就有 external field， 这是从哪里来 ？From the neighboring atoms or the host atoms, right? 我们的 gain medium usually 是一个 host crystal 再掺杂一些 dopant 进去，这是 dopant 的 energy level， 但是它会因为 host atoms， 对不对 ？For example, neodymium yak. Neodymium is the dopant, providing the energy levels. But yak, host crystal, provide a lot of neighboring atoms. They will exert external fields. That's why you have Stark effect. 所以你就会有比较宽的 bandwidth. Okay, good. Second question, why there is heat dissipation issue? Can you figure it out from this figure? Perfect. Yes. Relaxations between levels 2 and 3. Where is the potential energy after the relaxation? Right? It's non-radiative transition. So no new photons because of the relaxation, but phonons or thermal energy, right? 那这里就是会发热的地方。Okay, 这里是发光的地方，这两个是发热的。发热不好啊 ，and high power applications， 你不要小看这个 relaxation， 它会累积很大的热量在你的 crystal 里面。Okay, good. Any question? Okay, OPA provides a possibility to change your laser wavelengths. It has to satisfy with two conditions, energy conservation and momentum conservation. This is energy conservation. Just like this figure, absorbing one pump photon to virtual state, then releasing two new photons, one signal photon, the other idler photon. Okay? Energy conservation requires the pump photon energy equals the summation of signal photon energy and the idler photon energy. Okay. But we need to satisfy the momentum conservation as well. Momentum refers to h prod constant times wave vector k. Okay? I use a bold character to illustrate vector quantity. Okay? So just like this, your pump momentum has to be the same as vector summation between signal momentum and idler momentum. And this is the collinear geometry. Okay? If you shine your pump beam in this way, and your signal beam and the idler beam will co-propagate along with the pump beam. That's collinear configuration. And this momentum conservation has to be satisfied. But this is not the only possibility. Sometimes you can have non-collinear OPA or NOPA. Okay? In this case, your pump bin and the signal bin, idler bin, all of them propagate in individual directions. And the momentum conservation can still be satisfied with a vector sum relation like this. 只要你形成封闭三角形，这个是可以满足的。Okay. So either collinear or non-collinear OPA is possible. But can you identify what would be the problem in this case and the problem in this case? Let's look at this case. What's the problem? Can you really have this? In general, you can't, but you need to play something about phase matching, right? If these three bins are of the same polarization, like horizontal polarization, this is usually not possible because of crystal dispersion. 只要有色散，这三个向量又要同一个方向，通常这个向量和不会满足的。Okay? So maybe you need birefringence phase match to achieve this, okay, or quasi-phase match. But in that case, the summation between signal and idler momenta would be different from pump momentum. And you need the periodicity of your crystal to provide the artificial wave vector to compensate. That's quasi-phase match. Okay. What is the problem in the second case, non-collinear OPA? Yeah, walk-off. The effective interaction length is not just limited by the crystal thickness. 你可以发现这些并都走不一样的方向啊，所以只有它们重叠的区域可以发生 OPA 嘛，对不对？啊，所以它有效作用区不一定是，可能会比晶体还短。But there is some even serious problem about an OPA. You have strong spatial chirp. What is spatial chirp? We just talked about spatial chirp in lesson 7, right? Different colors appear at different positions in your laser beam. 好，你看这个样子。这个只画了其中一个 case. Remember, there are many different colors in your femtosecond laser beam. So maybe even your pump laser is of single frequency. Okay? And this is your signal. But there are many signal vectors. Different colors will be of different lengths, right? K equals 2 pi over lambda. For each lambda, you have one specific length. 所以你可以想象这个绿色的箭头有好多不同的长短哦，对不对？你是脉冲嘛？那假设紫色的真的就只有这样固定的，那么每一个不同长度的绿色箭头就要配一个不同长度跟方向的红色箭头，才可以组成封闭三角形 ，right? So that means your idler. Each color will propagate along different directions. Okay, so if you want to access the idler beam, you got some problem. If this situation is really serious, right? Okay, 所以有很多实际的问题在里面。But let's talk about the advantages of OPA. First, it is a once-for-all solution, not case-by-case solution. No matter what the desired wavelength you want to use, you can always use the same OPA design. Okay? All you need to change might be the wavelength of your seed pulse. Okay? The same pump laser, but you change the seed pulse wavelength, you can get different signal pulse at different wavelengths. It's a once-for-all solution. And besides, it involves with transitions between real states and the virtual states, not like traditional laser amplifiers. 传统的雷射放大器，你找到合适的 gain medium、合适的能阶，这些都是实体能阶，所以你的放大是 transitions between real states, no virtual states. But in OPA, it involves with virtual states. Okay? 那这样有什么样的弹性或好处啊 ？For example, the bandwidth is adjustable, sometimes broader than the real laser gain medium. Okay? It depends on the crystal and the pump conditions. So what I try to mention is if you use real laser gain medium, the gain bandwidth is limited by the material. Okay? But if you use OPA, you just use virtual energy levels, then the gain bandwidth is adjustable. You can make it very broad, broader than the real laser gain medium can provide, by choosing different crystal thickness, crystal type, okay? Choose different pump conditions, then you can do that. In general, a thinner crystal provides broader bandwidth. And a crystal of less dispersion, that means the index of refraction changes with wavelengths in a weaker sense. Okay, less dispersive crystal, you will have broader bandwidth. Okay, and usually if you pump your OPA hardly, you will have broader gain bandwidth. 所以这个是很多可以调控的空间啊。我要得到大的 OPA 频宽，我就选薄的晶体，色散比较不严重的晶体，我 pump 它 pump 的强一点，或者我 pump 它用更宽频的或者更窄的脉冲去 pump， 我通常可以得到更大的 OPA bandwidth. And besides, there is no heat dissipation, which is particularly attractive for high power amplifiers, right? Because there is no real transitions between real states, so there is no heat dissipation issue in OPA. Okay. And besides, it can achieve wavelength change and amplification simultaneously, instead of one by one. 你既改了波长，又放大。Just like this figure, the blue one is your pump bin, okay? And you have to prepare some weak signal pulse as seed pulse. Okay? After OPA, the signal pulse gets stronger, amplification, right? And there is a byproduct idler pulse. Okay? And the pump energy is split to signal energy, idler energy, and something unused. Okay? So this figure illustrates everything about OPA. Okay? Or you can look at the energy level diagram, which is quite understandable. Okay. Any question? But there are restrictions about OPA. First, it only produces smaller photon energies. Your signal and the idler frequencies are always smaller than the pump frequency. Okay? Or wavelength is always longer than pump wavelengths. That's the natural limit about OPA. Is there any solution? 我有一台 pump laser， 我要 OPA， 可是我想产生一个更短波长的这光出来，有没有办法？ Yes, good. You can try to perform up conversion for your pump laser first, like second harmonic generation, then you use the SHG bin to pump the OPA. You can have shorter wavelength output. Okay. We will see one example later. Secondly, for a fixed pump wavelength, the longest idler wavelength and the shortest signal wavelengths are limited by the crystal transparency. Okay. Not arbitrary. That is what I try to say. For example, if you use BBO crystal, the longest transparent wavelength of BBO is about 2.5 microns. And if you use Tai Sulphide laser of 0.5 micron as your pump, then your longest idler wavelength is 2.5 microns. But your shortest signal wavelength is 1.2 microns, okay, limited by the crystal transparency. So that means with this combination, you cannot create maybe 1 micron signal. It's impossible. The shortest one is 1.2, limited by the crystal transparency. Okay. And third, there is intrinsic loss. Just one example, still Tai Sulphide laser pump at 0.8 microns. And if you choose signal wavelength at 1.2 microns, then the pump to signal conversion efficiency must be less than 66%, because some of the power has to be contribute to the idler. Okay. 所以你做再好，你就只有66% in this case. So it suffers from huge intrinsic loss. 那随着你想取用的这个波长越长，这个损失会越严重。For example, if you try to harvest the idler bin, the same combination gives you a maximum efficiency of 34% only. Okay. So this is a big problem if you want to use OPA to get a really long wavelength. The intrinsic loss would be a limiting factor. Okay. And finally, OPA needs stringent spatial and temporal overlapping between ultra-short pump and signal pulses. Remember, in this scheme, everything is femtosecond. Pump pulse, signal pulse, idler pulse, all of them are femtosecond duration. So they can be overlapped in time and space with a very small margin. Any missing would be a big problem for femtosecond OPA. Okay. 那实务上，这个通常就是最考验这个 experimentalist 的地方。你要做好一个 OPA， 这件事是最困难的。